Hey guys, so we're going to look at probably our last part of probability. It's another way to check independence. It's using the multiplication rule. And if you ask me as a stats teacher, I kind of like this way a lot better. It's a lot easier when you can use this. You can't always use it, but it is powerful in that, especially when we know something is independent, we can use this rule. So just a couple things. Remember, if events A and B are independent, then the probability of A is the same as the probability of A given that B has happened. Because they are independent from one another, they do not change each other. So because B happened, it doesn't change A, and vice versa. Now also recall the formula for conditional probability. What is the probability of A given that B has happened? It's the probability of A and B over B. Now if you think about this, if you put this over 1, you can come up with the rule for multiplication here. The probability of A and B, if you cross multiply, equals the probability of B times the probability of A given B has happened. But we just talked about, well, if events are independent, then what is the probability of A given B has happened? It's just A. So if this becomes the probability of A and you cross multiply, now look, the probability of A and B equals the probability of A times the probability of B. So we get this formula. We can come to the conclusion that if events are independent, then the probability of A and B happening, the probability of two events both happening, just multiply the two probabilities together. If events are dependent, then the probability of A and B is the probability of A times the probability of B given A has happened, because now A happening changes B. This is like the deck of cards. If you take what's the probability of getting two aces in a row? 4 out of 52 times 3 out of 51. What's the probability of getting heads on a coin and a 6 on a die? 1 over 2 times 1 over 6, completely independent, those two events. So let's look at some examples of how do we use this new rule for independence. On a given school day, the probability that Nick oversleeps is 48%. So the probability he oversleeps, 0.48. And the probability that he has a pop quiz is 0.25. Probability of pop quiz, 0.25. Assuming these two events are independent. So think about that. Are they independent? Does him oversleeping have anything to do if a teacher is going to give a pop quiz? They're saying no, it's completely independent. So it says, what is the probability that he oversleeps and has a pop quiz? Well, look, these events are independent, so we're going to use our formula for independence. So that is just simply 0.48 times 0.25. That's a quarter of 0.48. That's 12%. Okay. Two drugs operate independent of each other. One does not affect the other. So drug A works 90% of the time and drug B works 80% of the time. If both drugs are given, what's the probability that neither drug is effective? So the probability that not A works and not B. Well, since they are independent, that's just the probability of not A times the probability of not B. And not in this case means they don't work. So the probability that drug A doesn't work, 0.1. The probability that drug B doesn't work, 0.2. That is what's 10%, is 0.02. So you have a 2% chance that both drugs don't work. All right. Given events A and B such that probability of A is 0.5, probability of B is 0.4, and probability of A or B is 0.8, determine if they are independent or dependent. And this is where this rule really is nice. Because if events are independent, then the probability of A and B should equal the probability of A times the probability of B. And if this works, then you're good. Let's check it. Does 0.5, sorry, oh, I read this completely wrong. I apologize. Well, no, that's still true. This is still true. But remember, this says or actually. So probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So now let's plug into here what we know. 0.8 equals 0.5 plus 0.4 minus the probability of A and B. So this right here, probability of A and B, 0.5 plus 0.4 is 0.9. For this to be true, for this to be independent, then when you multiply them, it should come out to 0.1. If you multiply the numbers A and B and you get 0.1, then it is independent. Let's see what happens when we do that. What is 0.5 times 0.4? Well, that's 0.2. So if you plug this in now, you'll see it will not work. Watch, 0.8 does not equal 0.5 plus 0.4 minus 0.2. So therefore, this cannot be the formula used. So this is going to be dependent. It's a little tricky. Okay, let's look at one more problem. A student is chosen at random from a student body at a given high school, and the probability that the student selects math as their favorite subject is 1 out of 4. Probability of math as their favorite is 0.25, 1 out of 4. Let's just leave it as a fraction because the other stuff will be a fraction. The probability that the student chosen is a junior, the probability that they are a junior is 1/16 out of 459. And if the probability that the student selected is a junior, or that the student chooses math as a favorite subject is 47 out of 108, okay, so the probability that math is their favorite, or they're a junior, is 47 out of 108. What is the exact probability that the student selected is a junior whose favorite subject is math? Okay, so we're looking for the probability that they're a junior and their favorite subject is math. Well, remember, they give us the OR statement here. The probability of A or B is A plus B minus the intersection. So now plug in. We got 47 over 108 equals 1 over 4 plus 1/16 over 459 minus the probability of A and B. And that's what they want us to find. They want us to find probability of A and B, so we just have to solve this. And this is from last we did this a few lessons ago. And it was on the graded assignment. So now you just want to subtract over and solve. It takes a little bit of calculator work, but that's fine. So I'm going to do 47 over 108. Okay, and then I'm going to take that, and I'm going to take answer minus 1/4. Answer minus 1/16 over 459. That's weird. Give me a decimal. And there you go. So you're going to get negative 0.0675 equals negative the probability of A and B. So what is the probability of A and B? 0.0675. Now, part B. Are the events being a junior and favorite subject math independent? Well, remember, if independent, then the probability of A and B should equal the probability of A times the probability of B. Let's test that now. The probability of A and B here, that they're both a junior and like math, 0.0675. Is 0.0675 equal to the probability that they like math times the probability that they're a junior? Let's just check that and we'll be done with the lesson for today. Is 1/4 times 1/16 over 459, is that equal to 0.0675? No, 0.0631. So 0.0675 does not equal 0.063. I guess it's 1 or 2. It really doesn't matter. Rounding correctly is 2. Therefore, the events being a junior and math being their favorite subject are dependent, right? Think about what that means. That means that if you know a student is a junior, it's likely that the likelihood that their favorite subject is math at this school is different than if you didn't know they were a junior. Okay? All right, guys.